final speaker for today is Tapio Schneider from Caltech, who works in the area of climate modeling. But I also saw that you do planet climate modeling too, so I don't know if you tell us about the climate on Jupiter. But, and he is also had served on the committee that brought the report, and is also funded to some extent by the Schmidt people. Go right ahead.
Thanks, Dan. Maybe to add to what Dan said earlier about serving on these committees, it's definitely service, and it can be a lot of fun. And when you're invited to serve on a committee, make sure you get a chair like Dan. It's, you know, you have a diverse set of people coming together, and we all have strong opinions, and it takes some special skills to come to a consensus study report in the end. And I think Dan was brilliant in bringing the perspectives together and actually getting a report that everyone could be happy with out of it in the end. And I learned from how Dan did this in the process as well, in addition to learning from everyone else about the fantastic things they were doing. So I had anticipated that Alex and Ilkay would give a better overview of the big picture than I could, and I'll focus a bit on climate and what I do with this group called CLIMA, the Climate Modeling Alliance, which is it's about 70 scientists at Caltech, at MIT, and at the Jet Propulsion Laboratory. What we do is just build a new climate model. The idea is to use data more extensively than other models, and ideally achieve a step change in the accuracy of climate predictions. Climate is changing, and we need to know how, and need to know what to plan for, and we try to provide that information. There we are. Background probably doesn't need a whole lot of elaboration, but useful to get us all on the same page. Climate has warmed about 1.2 degrees centigrade since the beginning of the Industrial Revolution. Here's the graph. You all have heard about the Paris Agreement, the goals to limit warming to some number, and that number is 2 degrees Celsius in the Paris report, or 1.5 as an aspirational goal. We already had 1.2 degrees, so there isn't that much room to go. And not only that, I mean, it's clear at some point we'll need to reduce carbon dioxide emissions. They haven't peaked yet. It's not quite the latest graph here, but you add the remaining the 2 years to this that are not on this graph. This is from the last IPCC report. CO2 emissions continue to increase worldwide. There is more energy produced with renewables, which is great, but the growth in renewables is slower than the growth in total energy consumption, so we're not even having reached peak emissions. Then if you ask, well, if you would want to limit warming to 2 degrees centigrade, you would need to cut emissions drastically. This is again based on the IPCC report. If you want to limit warming to 2 degrees, you would need to reduce emissions by about 30% by 2030 to have just a 2/3 chance of staying below 2 degrees. So emissions would need to peak before 2025. And this is from the IPCC report last year. They haven't peaked yet, and it doesn't look like they'll peak before 2025. If you want to limit warming to 1.5 degrees, emissions would likewise have to peak before 2025, and we would need to reduce them by 43% by 2030. Now, that's a nice idea. It's not, I don't think, reality. That's not achievable, given latency and energy infrastructure and the like. So that's the problem we are facing. I think in the best case scenario, we'll need to learn to live with about 2 degrees warming, and even that will be difficult to achieve. It'll be difficult to limit warming to 2 degrees. And this is 2 degrees in the global mean. That means a good bit more warming in high latitudes, for example. This is just from a climate simulation where 2 degree warming means spatially resolved in the mean. You have 4 or 5 degrees warming in high latitudes in winter, permafrost melting and the like. In general, you have more warming over continents and over oceans and so forth. And of course, if the mean warming were all there is, that's perhaps, okay is maybe too strong, but we have air conditioning, spread air conditioning, and 2 degrees is in some ways manageable, perhaps, if that were the issue. But that's not the issue. The issue is that 2 degrees warming means there are all sorts of other things are changing. Among them, as rainfall intensity is increasing, and that is already happening. As an example of Hurricane Harvey. 2017 in Texas. It's estimated that the probability of the rainfall that caused these devastating floods there increased by roughly a factor of 3, perhaps more, as a result of the global warming we already had. So it's very clear that we'll have to live with a different climate than what we are used to, and we have to adapt to it in some fashion. And to adapt, we need to know what to adapt to, and that currently is the challenge. Climate models have been quite successful in predicting the overall global warming we have seen. The models from the 1980s predicted well where we are now in the global mean. But now the question is, you need to locally adapt to climate changes. You need local information, especially about tail events, extreme rainfall and the like, and climate models just aren't good at this. I think you can think of there being a value chain going from data over models to what end users of various types in the end need to plan stormwater management infrastructure and the like. And there are breaks in two places. One is between data and climate models. We have a lot of data about the climate system. In fact, Tim, we get 50 terabytes of data per day from space alone. So there's plenty of data, definitely petabytes of data. Interestingly, they're almost not used in climate model development. They're used for evaluating climate models, just to hold the model next to data and say, oh my God, this looks bad. But they're only to extremely limited extent used to calibrate models. It's not done in any automated way. So I think that's the first broken piece in this value chain, and that's the focus of our work. I think there's a second broken piece, and that relates to what Ilkay was saying. If you want people to use scientific information, it's not enough to throw it over the fence. That generally does not work. IPCC is producing reports. The last one had 4,000 pages. You're welcome to read them. But as a planning tool, it's a pretty ineffective means of communication. You need tools in people's hands, and you need to co-develop tools with the people who need it, meeting them where they are, and that's likewise something we're not doing well as a community right now, but need to do better. There is, interestingly, an emergent industry trying to satisfy the market demands that now exist there. That's just happening in the last 3-4 years. But there is another gap that needs to be filled between models and what end users need. How good or bad models are, here's just one example from, again, this is also from the most recent IPCC report. You can look at this in various ways, but let's suppose you want to limit warming to 2 degrees. The Paris Agreement, so follow this 2-degree horizontal line in this plot. Here it is. And there are 2 different emission scenarios. For 2 degrees warming is not that much. It doesn't matter that much what emission scenario you're looking at, because that's actually pretty soon in time. But if you ask, when will we cross this 2-degree threshold? And you look at different models, you get answers between, well, interestingly, for some model, we crossed this threshold about 5 years ago. Well, that's not correct. There's these models over here. That's clearly not right. Models have large biases in global mean temperatures. But some other models, it's until the 2060s or so, even later, that we would cross this threshold. Doesn't strongly depend on the emission scenario, but it does strongly depend on what model you're looking at. It's just one measure of how uncertain even global mean predictions are. Unacceptably uncertain, in my view. That's not useful for deciding how big a storm drain you should build in Ann Arbor. Again, global mean is a good proxy for talking about climate change. It's not what you ultimately care about, but it's a good proxy because just about any climate impact that you will look at, it scales with global mean temperature change. Here's one example. It's the percentage change in heavy rainfall in Southern Asia associated with a monsoon. On the y-axis and the horizontal axis, the global mean temperature change for different emission scenarios at different times in the simulation, so at different carbon dioxide levels, if you wish. And the point is there's an almost linear scaling of an impact, intensity of rainfall, with global mean temperature. So uncertainties in the global mean percolate in just about any impact you will look at. For precipitation, we understand, well, why having to do with the physics of precipitation, basically scales with temperatures. But these global predictions we have to get right, and then we have to get the local predictions right. And if the global ones aren't right, then whatever you do on small scales won't be right either. So why are climate models are doing relatively poorly? And I should say, in the big picture, they have done well. Predicting global mean temperature change is not so bad. the change. The temperature itself, there are large biases. So if you look at the temperature right now in the climate model, you get very different answers from model to model. But if you ask what is the delta T over the last 30 years, the models do pretty well in giving you about the right answer of what we have seen. So the big uncertainties in climate models come from small scales. A climate model has a horizontal resolution typically of 100 kilometers, going towards tens of kilometers, and there are a lot of things falling through the cracks of the computational mesh. Clouds are the most important among them. Clouds dominate uncertainties in climate projections. They cannot be resolved. You know, the clouds you see out here, the dynamical scales of the air motion that generate them of order tens to hundreds of meters in this case, it's far away from being resolvable in a climate model with even at resolutions of tens of kilometers. So we have to parameterize these models, meaning the models for clouds, we have to express what clouds do as a function of things we can resolve, temperature, wind on the grid. And that's typically done in some ad hoc way, some of it going back decades. It's just sedimented history of some ideas someone had 50 years ago. So that just gets embedded. Because these systems are very complex and complicated, people have been very hesitant to upset the apple cart there. If you take one piece out or change one piece, there are nonlinear consequences for all sorts of other pieces usually. So there's an extreme risk aversion to larger changes, because if you make larger changes, most likely you won't have a climate model that works for a while. And if you're a climate modeling center, you can't afford that. It's just the political reality of how funding works. When I started getting interested in these smaller scale problems, I did work on other planets, on large scale fluid dynamics. I needed to convince myself that this will remain an interesting scientific problem for some time, because I didn't want to work on something that disappears as a scientific problem in a few years. So I collected data on the peak performance of the fastest computers going back to 1979 in this case. That was the first climate assessment. It's an important date for my field. And you know, computer performance has increased exponentially consistently. We all know it's Moore's law driving that. It's a bit more interesting than Moore's law, because the exponential increase has kept going even as Moore's law has reached saturation. Massive parallelism has still led to exponential increase in peak performance. So flops double about every 1.2 years, and Suki Manabe was one of the Nobel laureates last year for the first climate model that he built. That was in the 1960s, late 1960s. The first coupled climate simulation in the 1970s. So since then, computing power has increased by a factor 10 to the 9. Are we a billion times better than Suki Manabe was? I think not by any reasonable metric. So here's what climate models have done. This is climate model resolution, the horizontal resolution of an atmospheric component of a climate model expressed in inverse kilometers since the same time. So these are all models published until 2017 when I published this graph, and I should update it, and we'll do so soon. But the basic picture is this. Flops on the right on the log axis. On the left axis is resolution in inverse kilometers, also in a log scale. And the two log scales are related such that a factor 10 on the left corresponds to a factor 10 to the 4 on the right, because if you want to uniformly increase resolution by a factor 10 in a three-dimensional fluid simulation, you need 10 to the 4 times the compute. 10 to the 3 for space and another 10 for time. So if all increases in computing power would have gone into increasing resolution of climate models, the climate model resolution should have followed the blue line. And it did not. To the extent there is any line, climate models fall on the line with a shallower slope, meaning that the marginal increase in compute we've had, about a factor billion in the last few decades, has not all gone into resolution of models, but in fact much has gone into complexity. So the models plotted there are AGCMs, or atmospheric general circulation models, AO, atmosphere ocean, ESM are Earth system models. The models have grown in complexity. Now we have detailed models of a land carbon cycle and the like in these climate models. It all takes some computational resources, and I think it has enabled new science that was probably a good investment. We could have gotten a bit more resolution had we invested more in that, but we have invested a fair bit into model complexity. But suppose now we decide enough complexity, we just put it all into resolution, and when our scientists not needed anymore to solve the problems I was just talking about. So we are approaching this gray shaded area, what's called the gray zone for deep convection, where you marginally begin to resolve thunderstorm clouds, 10-kilometer scale motion to maybe 1 kilometer. But the clouds that are crucial for Earth energy balance, clouds over tropical oceans especially, they have dynamical scales of meters to tens of meters. So it doesn't even fit on the graph, but if you would suppose that computing power continues to increase exponentially, that we put all of that into resolution, by the 2060s, we would be able to explicitly resolve the dynamics of low clouds. So that's far out. Computationally, we're not going to solve this problem. It's a factor 10 to 11 increase in compute you need. And even once you can do that, you still not resolve how snow crystals, ice crystals, droplets, and the like form. That's obviously also important. So computationally, this is not going to be solved in any brute force way. So scientific ingenuity and you are needed. So clouds are the big problem, and just to illustrate the complexity of a cloud that matters, here is just the droplet scale physics in a cloud, and there are all sorts of words there, of processes that go on, and they all matter. They all matter for determining optical properties of clouds. There's aggregation of droplets, nucleation of droplets, and the like. Those processes happen on scales of micrometers, nanometers, and what we in the end want is information on the scales of, on macro scales, 100 kilometers, what are the optical properties of clouds on these large scales. And we somehow have to bridge scales from micro nanometer to tens, hundreds of kilometers by using what we have at coarse resolution, temperature, humidity, and the like, to get what is the emergent property of a cloud in albedo, average cloud cover, and the like. And computing is not going to do this, at least not alone. So we live in the golden age of data. We have about 50 terabytes per day of Earth observations. We have a good 40 years of excellent data on Earth, not quite as much on clouds, but on other properties of the Earth system. There's really many amazing data sets coming around. This is LIDAR and radar, space-based, that for the first time gives us global views of clouds and their properties like droplet-sized distributions. We can even do things like see Earth breathe from space. This is from my colleague Christian Frankenberg. It is a measurement of what's called solar-induced fluorescence. It's a proxy for photosynthesis of plants. So it's of the rate of photosynthesis, so it tells you how much carbon a plant takes up. And you can see the seasonal cycle of the biosphere. You can see Earth breathe. And it's the first time since a few years ago that we have such data. It allows us to disentangle two big terms in the carbon cycle, photosynthesis and respiration, that we could not measure separately on any large scales. Now we can measure photosynthesis or a proxy for it separately. And it's really game-changing for what we can do in modeling the land biosphere. So we have all these data. We also have computationally generated data. We can simulate clouds in small domains. So there's no way to simulate clouds globally, but we can do it pretty well in domains. I used to say a few kilometers on the site. I was working on a project with Google collaborators that we just submitted last week. We have now done these simulations with a few hundred kilometers on the site, meter scale resolution. It's things you can do if you have a bunch of TPUs at your disposal. No way to do it on the globe, but you can do it in limited domains, and these simulations are very good. So this is just a visualization of a cloud. Blue is rain, gray is the cloud, and at the surface it's buoyancy, or essentially temperature. And these simulations we can compare with field studies, and we know they're good simulations by comparing with aircraft data, for example. We can use those as well. We can generate data computationally. So this CLIMA project was funded to capitalize on the opportunities at the intersection of computing and data. It's clear that computing alone is not going to solve the problem. It's also clear to me, at least, and I hope I'll try to convince you in the next few minutes, that data alone is also not going to solve this. But if you combine computing and data and theory in much the way that Alex laid out, I think we have a real shot at progress here. So CLIMA by now is about 70 scientists, applied mathematicians, and engineers working together, literally elbow to elbow. At Caltech, we were out of office space, so I asked the provost whether we could use the former provost's house as office space, and after some convincing, we got the former provost house as office space. Where literally you have computer scientists and earth scientists all staying together, and it really helps foster collaboration across disciplines that otherwise it's not so easy to make happen. So it's clear, I think, that data are part of the solution, but how? Climate is quite special, but maybe not special for a scientific problem. I think there are three issues that matter for science and for using any type of machine learning and science that matter less for other applications. One is we need to predict the climate that none of us have seen. We have no data for it. We need tools that generalize well out of the sample of observations. And we need models that are interpretable. And I think it's not just a nice thing to have. I think it's critical. Because in the end, you want people to use the tools we develop to make decisions about stormwater management structure or building seawalls or making policy decisions. And if it's just a black box that produces something that you can't otherwise easily verify, say in 10 years this will happen, but how do we know that's right? I think you need to have a clear story, ultimately a science story that supports that prediction. It needs to be interpretable in that sense that the model can be trusted. And you need uncertainty quantification. You want not just a point estimate, but a range of estimates with probabilities attached to it. So these are three things that I think are crucial across scientific fields that machine learning tools are not doing all that well at usually. Let me just give you one example of something that's been done in climate sciences that I think was valuable, but I think it's not ultimately a long-term success story in my view. What people have done is try to use supervised learning approaches, the standard things you can do with PyTorch and TensorFlow and the like out of the box, to learn convective tendencies, so the temperature and moisture tendencies induced by motions in clouds. And what you need for that is labeled data, input-output pairs of data, so input temperature, humidity, output the time derivative thereof due to a cloud. And we don't have that data observationally. In fact, there's no way of getting it that anyone knows of. You can't measure the detailed dynamics of a cloud directly, not from space, not from an aircraft, not by going there. So what people did is use higher resolution simulations and essentially build emulators of the simulations. And you can do this quite successfully. So here is, on the right is just a higher resolution simulation of this convective heating rate. On the left is the same thing from a neural network. And these tendencies, same for moistening, these tendencies can be captured quite well. So you can minimize some loss function over the tendencies. You can drive that to near zero, and you have something that captures these tendencies. At least it emulates a model. That model itself is not perfect. In fact, it won't be great because it still doesn't resolve all the small-scale processes. At least we can emulate it. But there are various problems with the approach. I mean, one is it doesn't generalize out of sample well. So if you try to use the same model in a different climate, it tends not to work well. It's hard to do uncertainty quantification. It's hard to interpret. And there are also practical problems. If you learn a model like that, and then you put it back in a climate model, the climate model is typically unstable, and the like. So it's worthwhile doing. It's sort of what you can do with off-the-shelf tools, but it's, I think, not ultimately what we want. So if you want generalizability, interpretability, and UQ, I think the way forward is to combine the best of both worlds. Science as we have done it for a good 400 years at least, reductionist science with data-driven approaches. Reductionist science has been extremely successful. If you would want to reduce it to one reason, I would say it's parametric sparsity. Newton's law of universal gravitation, it's one parameter law that captures all sorts of things about the universe, apples falling from a tree, planets orbiting stars, and the like. But it hits its limits in complex systems. We would like to have something like Newton's law for a cloud, but don't, and I have tried, and many others have tried. We haven't been successful with that approach in extremely complex systems. Deep learning success, by contrast, rests on overparameterization. You are in a regime where the number of parameters typically exceeds the sample size. It leads to very expressive models, but also very data-hungry methods. And as a result of that, generalizability, interpretability, UQ is difficult. So our approach is combine the best of both worlds and make progress. You can, I don't know what the right word for it is. There's some physics AI hybrid approach, perhaps. Sometimes people say physics-informed AI. I don't like that too much because it's kind of the other way around. AI-aided physics is maybe the better way of looking at it. Let me try to make this a bit more concrete how it goes. But there are three legs to it. Theory needs to be driven forward because what theory gives you is parametric sparsity. Use physics, biology, chemistry where you can to reduce the demands on data. Basically, domain-specific knowledge is important. Incorporate it where you can because it reduces what you have to learn from data. We need to harness diverse data, multi-fidelity data, data that's noisy, data that's sparse, for calibration and uncertainty quantification. And the observational data we have alone are not quite sufficient. You can make quantitative arguments about it. While we have a lot of data, the number of degrees of freedom in a climate system, just atmospheric turbulence alone has about 10 to the 30 degrees of freedom. No way you can constrain that from data alone. So you need to leverage computing power, A, to generate data computationally, training data computationally, and B, to run models at the highest resolution you can. And the cartoon view is perhaps this, that you have this Navier-Stokes equation with some sort of Reynolds stress that you need to learn from data. And the data we would use are observational data, space-based, ground-based, and data generated computationally in these limited area simulations that I was already mentioning. So what matters in climate, what you want to know is statistics of the climate system. You want to know the probability of an extreme rainstorm 20 years from now, or the probability of having snow in January in an arbor 20 years from now. Don't quite know what it is, but I know it's decreasing with time. The point is it's statistics, and that means that your loss function that you use for calibration of the model, ideally, is also based on statistics of the system. That's what we have, 40 years of data that we can aggregate in time, in space. So that's quite different from the supervised learning that I mentioned before that uses instantaneous data, trajectories, if you wish, of the system, time tendencies, time derivatives, and the like. Spatial smoothness of the statistics overcomes an often cited problem that the resolution of observations and simulations don't match. Statistics vary smoothly in time, resolution becomes less important. So in other words, if you have a thunderstorm cloud, whether it's here or 10 kilometers from here, will look very different. If you look at statistics of thunderstorm clouds, it will be a smoothly varying field on larger scales, and it smoothes the objective functions. And it focuses on what matters. There are two problems with using statistics to learn from. One is that it basically eliminates supervised learning as the approach to take here. You need to treat learning from data as an inverse problem. Now, we have a lot of technology for doing that, Bayesian inversion and the like. There is no reason not to learn even neural networks in that way. The challenge is that standard approaches to treating inverse problems, Bayesian inverse problems, require many forward model evaluations. Typically 10 to the 5, 10 to the 6 would be typical for, say, Markov chain Monte Carlo. You can't do that with a climate model. You can't run it a million times for decades. So you need the evaluation of the loss function is expensive, and you need methods that are computationally very efficient to make this possible. Let me just give you one bit of intuition of what kind of statistics I'm talking about. Here's just Arctic sea ice extent in colors from different climate models, and in black are observations, and it's just the seasonal cycle averaged over 30 years. And this is the area of the Arctic covered by sea ice in millions of square kilometers. The key thing you see is, well, there's a seasonal cycle. There's a minimum in September, there's a maximum in March. But the amplitude of the seasonal cycle and the baseline of the seasonal cycle varies widely among climate models. It's almost a factor 2 difference in sea ice cover among climate models. And in fact, the difference is so large that if you ask, when is the Arctic ice free in summer for shipping through there, you get different answers from different models. The spread across models, more than half of the spread across models is driven by the present day bias in sea ice cover. I mean, simply put, a model that has a lot of sea ice right now just takes longer for that sea ice to melt. That's the bottom line. But we have observations, and so you have a large mismatch for many models between observations and what they simulate in the seasonal cycle. The goal would be to use that mismatch to learn about uncertain processes here involving cloud, boundary layer dynamics, maybe sea ice, to drive this bias to, well, 0 would be nice, or consistent with observational noise is the point. The bias is larger than the signal we want to predict. It's not untypical for climate statistics. The arrow gives you about the change you would expect by 2050 and the various climate change scenarios and the observed sea ice extent. And you see that the bias of the models is of the same order or even larger than that signal. That's not comfortable. Okay, so how does it work? You need to treat learning about parameters as an inverse problem. And one way we figured out to do it that's computationally feasible is the following. We essentially use Bayesian learning ideas, but we make them up a factor 1,000 faster than they used to be by combining them with machine learning emulators. And just to give you the gist of how that works, Y, here are climate statistics, say sea ice extent in the Arctic. G of theta is the climate model simulating those statistics. Theta is a set of parameters, can be parameters in a neural network or just scalar parameters appearing in the model. And eta is some observational noise. Because we're looking at statistics, that noise is plausibly Gaussian, so a central limit theorem argument. And we use variants of common inversions to essentially solve the inverse problem, if you wish, of inverting for the parameters given the statistics. What common inversion does is it avoids the use of gradients. You have an ensemble of particles, parameters that you propagate forward and in some pseudo time of a dynamical system. And what you get out are pairs of parameters and data, theta and y. And what common inversion does is essentially solve a high-dimensional experimental design problem. Theta can be a very high-dimensional vector, several hundred-dimensional. And what you want is place points in this several hundred-dimensional space so that they cluster near the posterior, the maximum of the posterior density. And common inversion does that very efficiently, that it clusters points in the vicinity of that posterior maximum. It usually needs something like 5 iterations, maybe an ensemble of size 100, so that gives you 500 forward model evaluations. It gives you 500 pairs of parameters and data. And on these 500 pairs, you can train an emulator. Say with Gaussian processes might be one option, but it could be neural networks. We are currently doing it with random feature models. There are all sorts of options for doing that. Then you have an emulator that you can train at the cost of what this common inversion takes. And that emulator is very cheap to evaluate. It's a map from parameters to statistics. We can evaluate them 1,000,000 times in minutes. So we can sample from the emulator. We can use MCMC on the emulator to get posterior densities. And perhaps in the interest of time, let me just say it works. Just to say maybe one thing here is here's just one example from a two-dimensional parameter space, and it doesn't matter what the parameters are now, but it illustrates one generic feature. Common inversion clusters points in the vicinity of the posterior maximum, and the points here are these black dots, but it also collapses the ensemble unless you do special things to it, meaning it underestimates uncertainties. However, you can train the emulator in the process of this ensemble collapsing, sample the emulator, and that's what you get in these contour lines. Here's the posterior probability density that is much wider than the collapsed ensemble, and in this case gives the correct probability density. This example is simple enough. We can test it with brute force methods. Just to say, maybe the key take-home points for other fields here are these. This is a method that doesn't require gradients of the model. You don't need to know any derivatives. You can treat the model as a black box. It's nice. It's easy to use in that sense. It gives you uncertainty quantification, and you can use it for even training neural networks, deep learning models, and the like. I'll show you an example how a bit later. So you can do all the things that people usually want to do with supervised learning approaches, gradient-based approaches, with this method in a computationally efficient way. That's perhaps the bottom line. And if you want to use it in your field, we have worked hard to make the software nice and easy to use, and it's on our webpage. You can download it, and nothing ever is completely black box, but it's fairly close to simple to use. So what we are doing at Klima is building a neural system model in which, in the end, all components jointly learn from data. What we're doing, we have an atmosphere model we're developing at Caltech, an ocean model the MIT group has developed. There's a land biosphere model we're developing at Caltech, whole land model and the like. There's all the traditional components of a climate model we're putting together. And wrapped around it is a layer of machine learning data assimilation tools that are to inform the components with data. Observational data where we have them. We're doing this for the land biosphere, for example, currently, or computationally generated data where observations alone aren't enough, and we're doing this for clouds as one example. I wanted to give some details how, just to put a bit of meat to it, if you want to translate a similar approach in your field, in big pictures, how would you do it? And well, let me try to sketch it out briefly without getting into all the details here. So clouds are subgrid scale phenomena. They're below the grid resolution of a climate model. And the first thing we did is just theory. You use homogenization theory approaches to take the equations of motion, like a Stokes equation, and conditionally average them. Averaging means you lose information, and you get equations. Fluid dynamics folks among you they will look vaguely familiar. For the others, not terribly important what they are. But these are hyperbolic conservation laws. Here's one for mass or density, and here's one for some scalar phi. And the left-hand side for fluids people will look familiar. That's just a conservation statement. But the right-hand side is what happens once you average. There's just functions appearing. In this case, something called entrainment, detrainment, which describes the mass exchange between the cloud and the air around it. That appears as a result of averaging, but we don't know what that function is. That's the information we have thrown away as a result of averaging. And what fluid dynamics has done since Prundel's time, for a good 100 years, is reduce problems to functions we don't know, guess what these functions may depend on, ideally non-dimensional quantities, and then people go out in the field and measure those functions. Go to Kansas wheat fields and measure turbulence in the boundary layer, classic study. We're doing essentially the same thing here. We reduce it to functions we don't know. We learn those from data, except instead of going to Kansas, we use computationally generated data and Earth observations broadly. So these closure functions that appear are really great targets for machine learning approaches, for all sorts of machine learning approaches. You can use dictionary learning, neural networks, and we have tried a number of approaches there. But the key point is they're embedded deep inside, in this case, a system of partial differential equations. And you don't have labeled data that are informative about the functions. You have data, say, about mean cloud cover that depends on the mass exchange rate of clouds with their environment indirectly, but you do not have direct data on the mass exchange rate that you want to know. So the challenge is to learn from these indirect data using these inverse modeling approaches. And you can do it. And it, in fact, works extremely well. So what the physics gives us is a hypothesis set that is expressive enough. And it reduces what you need to learn from data to relatively few functions in this case. At least for physical systems, this works well. Biology, I thought you can't do this. Turns out, actually, plants are fairly physical too. So there's quite far you can go with thinking about plant hydraulics and physical equations for photosynthesis and using similar approaches. But you hit the limits at some point. So now we need to know what these closure functions are, and we choose sites with large biases in current climate models. Here's a simulation from an existing climate model, and it shows the bias in cloud cover. So it's a % bias. Blue means too many clouds, red means too few clouds, and there are many places, like where I live out here over the Pacific, you have biases of 50% and more in the mean in cloud cover. And what we did is choose some sites where these biases are large, conduct high-resolution simulations driven by a climate model to generate data, learn closure function from the data, and then we have a complete model, which as an ancillary benefit is guaranteed to be stable because we focus on the statistics we want to predict in the end. So as long as you simulate the statistics, the model will be stable. We talked a fair bit, Alex talked about the closed loop automated science. You can automate this entirely. We haven't entirely automated, but what we have done is solve the experimental design problem of asking where should you do a simulation so that it maximizes the information about the things that you're uncertain about. And here's just an example of what comes out. This is some utility function. Ooh, shutting down. That's just a pretty brutal way of ending. I can tell you the rest though. This doesn't look good. I don't know. This just says shutting down. But I can keep talking. It's okay. So you can solve this experimental design problem and in principle automate the whole process of generating a high resolution simulation, generate new data where you most need it, inform the model, use the updated model to ask what is now most uncertain and repeat. And it works extremely well. You have to take my word for it. We have fantastic simulations of clouds in a low-dimensional model in the end that you embed in a climate model. So this model is something like a factor 10 to the 8 faster than the high-resolution simulations and captures cloud cover, like subtropical cloud cover, where existing climate models have huge problems extremely well. And we pursue the same approach for all other components of the climate system. So for example, for the biosphere, I mentioned we have a biophysics model, and we have data like the solar-induced fluorescence data from Christian Frankenberg and his colleagues, and we use the data to calibrate what we don't know about the plant model, and that likewise gives us very good simulations of carbon uptake by the plant biosphere. And I think I wanted to tell you something. I know there's a lot of machine learning types among you, so these are some examples of machine learning that's not quite the machine learning that you have seen. So these entrainment functions, for example, we use neural networks there, but trained in an inverse modeling setting, so with common inversion, without gradients, and you can do it, and it works well. You can do all sorts of other approaches. There are technical questions that some of you might ask, how do you get to high-dimensional parameter spaces in neural networks with ensembles of size 100? Happy to talk about it. You can do it. And I think I had two slides that I maybe just can't say a word about. That's more traditional machine learning because it maybe helps connect with some of you data science folks. In the end, what you get is a climate model that produces better simulations, but the simulations are still fairly coarse in resolution, right? There's maybe 10 kilometers or so is what we can achieve. But again, what we want is inform people for how to adapt to climate impacts. And what you need to know there are really small scale things. You want to know about flooding on the scale of streets. And that's not something a climate model can do, but a climate model can provide the back-end information to get there. And then what you need to do is translate the coarser resolution back-end information into high-resolution flood maps, for example. And that, I think, is a very good application for generative models. It's essentially a super-resolution problem, a bias correction and super-resolution problem that you can solve with generative models. And just want to put this out there. If people want to work in this area, I think it's a great area for working with those types of tools. And why? So essentially, the problem you have is you have a climate model simulation that, say, for the sake of arguments, 10 kilometer with pretty high resolution, but you want to know something about flooding, precipitation on the scales of tens of meters. What you don't have are paired images. What you don't have is a simultaneous simulation 10 kilometers with simultaneous verification data at 10 meters. What you do have are statistics at 10 kilometer, and you have observed statistics at 10 meters. But you don't have them in pairs. The chaotic nature of the climate system makes it impossible to exactly match trajectories. So it becomes a bit like the problem of translating horses into zebras, if you have seen these types of papers, right? It's an image translation problem. You want to get the statistical properties of the image right without having direct pairs of horses and zebras that look exactly identical next to each other. And so the horses to zebras problem is solved with generative models. You can do it with generative adversarial models, with diffusion models and the like. And I think that's a good application for downscaling problems. I think on science, that's probably what I had to say there. And if you get the screen back, I can show you some pictures. But if not, you take my word for it and you look at papers. Maybe a few concluding words and bigger picture issues. I think for this work to succeed, it takes diverse expertise, what Ilke mentioned. We have computer scientists, we have numerical analysis types working with climate scientists, and any one of these expertises alone will not suffice. You really have to bring it all together. And bringing it all together is challenging. And I think Dan was saying it well over lunch. You need to work with people's self-interest, and they're not necessarily convergent always. If you want to write machine learning papers, it's much faster. Obviously, machine learning is rapidly moving, but it's much faster to work with simple dynamical systems than with something as complex as a climate system. And yet, these are the real problems we need to solve, and you need to work with people's incentives that they get their publications on interesting methods while making an impact on interesting problems that perhaps need a bit more longer-term thinking. I think we succeeded in creating a culture where this collaboration works well. People Some of the team said this is the best work environment they have ever been in and ever will be in. And that's fantastic. But the challenge really is to align this type of work, align this type of work with career options for early career scientists. It's not always easy. I think people love doing the work, but it's not what most naturally leads to your faculty position, for example. And yet, I think the approach is the way to go. I think the success we've had it is in some ways a proof of concept that these, in this case, physics-based models augmented with AI tools are really achieving a step change in accuracy and simulating clouds, land biosphere, and the like. That's what we wanted to do. The people love doing the work, but it's not an easy thing to make it happen at universities. And maybe I'll leave it at that, and we can talk more about it. How do you, the convergence we talked about, using AI tools in the sciences and for the sciences, how you make this long-term successful is probably a good discussion topic. So I'll leave it at that. And sorry about the remaining slides, but thank you.
Yeah, I'm sorry too, but maybe we'll get them up and maybe they will be posted or something. Yeah. So we will have time for questions, and then we can open it up to questions of our former speakers as well. I hope that you're all inspired by the passion for impact that you're seeing in all of these projects. And as Tapio and Ilki and others have said, it's the basis of good technology, good science, but it's also the alignment of unique components and collaboration and building synergy that really lead to impact. And for those of you that aspire to membership in a national academy at some point, my experience is you don't get in for just a long resume of a lot of the papers. You get in because the community can say, person X did this, and maybe that really changed the world. So it's this kind of work that really ends up counting. So let's open up the floor for some questions of Tapio. Please.
Thank you very much for a very critical talk. I just want to sort of jump on your end comments that we need to broaden out our discipline base. For example, we're referring to the Arctic, where most of the warming is taking place. I think we need to consider vegetation dynamics. In other words, vegetation is growing taller and bigger diameter. How does that affect transpiration effects? And also the soil microbiome composition, and how does that affect the nitrogen fixation and carbon removal? And the second point I wanted to make is the climate that we're going to experience may be unprecedented in human history, but it's not unprecedented in the Earth's history. So what can we gain from looking at the paleontological data as far as expected trends? Thank you very much.
Yeah, all good points. I agree with all of them. So what can we gain about the past? Maybe go back to Jupiter or the other planets. I loved working on other planets, primarily because it was a good test of your intuition and understanding, in this case, of fluid dynamics. You would just go to parameter regimes that are far different what Earth has. And then you have a few data points, very few. For Jupiter, you see a little bit, cloud layer on the top. You know very little about what's going on underneath. But you have a few data points to see whether what you said is at all plausible. It's not enough data to really learn a model from. And I would say the same about Earth past. Absolutely right. Climate change that is coming it is fast, but in amplitude small compared to what has happened over Earth history. But the data are extremely sparse going back. So the data, I think, will be good to say that your model is wrong if it's wrong, but they're probably not good enough to say, well, this is really right.
So we have your slides.
Yeah. I mean, rather answer questions. It's just awkward to go back now. But
Hi, Tapio. It's
Well,
good talk.
wasn't there one or two you wanted to show?
Yeah.
Yeah, okay.
So I want to ask a question about the in terms of the forecast versus projection, because for the weather forecast we have made quite a success using the ensemble forecast technique. So if we want to do a climate forecast instead of just a projection, in your opinion, when we develop such AI-aided climate model, will that make such ensemble forecast simpler or more complicated?
Yeah, that's a good one too. So my take is we need uncertainty quantification, and the way you quantify uncertainties is to estimate posterior densities over parameters, sample from those posterior densities to run ensembles of predictions forward, right? And that will give you uncertainties and a projection quantified based on the data we have, and that's I think what we ought to do. So, then the question is, how big an ensemble do you need? If you talk with people in the insurance industry, when they do hurricane risk estimates, they run like 10,000, 20,000 simulations with pretty cheap emulators. Now, that would be nice, but you can't do that with a climate model at tens of kilometer resolution. So the compromise, perhaps, is that you need something like hundreds of simulations, but rigorously drawn from a posterior density over the model, that you have rigorous uncertainty quantification through those. 100-dimensional ensembles, maybe not spanning the entire, in principle, high-dimensional space, but I think it will give you a pretty good idea on key things like precipitation extremes and their uncertainties. And I think that's the way to go, which is maybe part of why you were asking, in my view, an argument against going to the highest resolution model you can build, where you can run it once and you don't know what this is good for. Yeah.
Thank you, that's really interesting. You talk a lot about scaling up the input data and the simulations for what are going into the models, but can you comment on scaling down the outputs? Because currently we're getting like mean global temperature or like the bioclim outputs, or however many global arc minutes the outputs are.
Yeah.
Is because it's a global issue, it's also affecting smaller scales, so we need smaller scale outputs from these.
Maybe that was
You can change your
You can
mind.
turn on that slide. Maybe I can show that one slide that you had there in the end. I can say. So I think there are two pieces to the answer. One is that you want to downscale things that in principle you can resolve, like temperature, even to some degree frontal systems. So here's just one example. This is a cartoon of it, and here's sort of a 2D flow. This is 2D turbulence with a tracer. It's like precipitation in it. This is a high resolution simulation. This is a low resolution simulation, and this is a generative model turning horses into zebras. So this is taking the low resolution and turning it into high resolution. So I think number one is you can use generative models, AI tools for that downscaling. For problems where you have the relevant data, where the necessary information is encoded in what the climate model puts out. But then there are other problems. So hurricanes would be a good example. If you're at resolution courses and say 25 kilometers in the horizontal, climate models have no hurricanes at all. And so there's no way to downscale something that isn't there in the first place. So what you want to do in that case is build a hierarchy of models, that you build a hurricane model that runs on the climate model, give them a boundary condition, and that hurricane model. What the insurance industry does is use statistical models for that, or you can use generative models for it. So Kerry Emanuel has been doing this for a long time with the statistical models that incorporate some hurricane physics for intensity. Run that on top of the model, and then you can do your 10,000 hurricanes. So that's a slightly different problem. Same, I would say, with storm surges. No way to do it in a climate model. You just need a hazard model for the hazard you're interested in that's running on top of the boundary conditions provided by a climate model. And then for what you really want to know is how will this impact the house down the street, so then you need the catastrophe model added to that in addition to it.
Thank you, Tapio, over here. Wonderful talk, really inspiring. I'm going to start with a little anecdote that one of my colleagues here, Carrie Pratt, has built a mass spectrometer that can capture atmospheric data, and last 2 years she's figured out how to make it see chlorine radical. And here in the Midwest we have a lot more chlorine radical than you would expect. We've just seen it now in January and February. It's more like coastal you would get the chlorine radical from the sea, but it's because we put rock salt on the streets all over the Midwest. And so that was like not an observation. And so I was thinking as you were showing this plot of like the blue line of computing power going up and the data available going up, but how does like new observations and theory, do those kind of grow in the same way and contribute, or do you get like a step change of a new theory or a new observation?
I mean, in theory, I think there definitely are step changes possible. That's, again, let me answer that quickly. That's an interesting cultural thing. I think all these small-scale processes, these prioritizations, they were considered uncool scientifically. That's just something that's done in climate modeling centers. There were very few grad students touching that. It was considered kind of a messy engineering problem. And I always felt, you know, there's people like Suki Manabe who won the Nobel Prize, and R.Q. Arakawa, a contemporary of his at UCLA. I mean, and no one, I think, would call them just climate modelers who were just tweaking stuff. They were doing foundational science that made possible to do. And I, for a good decade, I think I've been saying we should view this as fundamental science, which is what it is. And then you can achieve step changes on the theory side. And I think we have done that with some of the things we have done here. On the observations, so step change and observation, there's two pieces to it. What matters for climate are statistics, right? It means statistics accumulated in time. There's this old quip, you know, a climatologist is someone who adds 30 numbers and divides by 30. That kind of captures the situation of 30 years of data. The corollary to that is that if you have new data, the incremental value of those is relatively small because they only become valuable as you accumulate statistics, right? The polar orbiting satellites we have for clouds, it's fantastic that we have the first 3D cloud data. They're actually interesting. They're not used for weather forecasting because it's too rough in a salinization problem. And I think you can argue the data are underused, but they become valuable as you accumulate statistics in time and can use them in the way that I described. But the consequence is that, you know, the value you add for a new data product, you would expect it to be less than 1% per year. Less because there are many other data already out. Now, could there be a revolutionary measurement where the value added is much bigger? In principle, possible. So things like you would really like to know the turbulence statistics inside a cloud or the detailed distribution of droplet sizes in a cloud. So if you could figure out how to measure that, I think that would be game-changing fast. But no one has any idea how to do it. There hasn't been any dramatic step change on the physical side of things. I would say, you know, the things like what Christian did with solar-induced fluorescence, it's completely changing what you can do for land modeling. So there are some examples where observations become game-changing. But on these sort of thorny old physical problems, it's not on the horizon.
One more?
There's a question over here.
Thank you. Hi, I'm Elon. I'm a visiting PhD student at SEAS. So when I think about the inferred parameter space from machine learning, I can imagine that they look very different over space and time because of over-parameterization, identifiability issues. I usually think of that as a drawback because wouldn't it be nice if the parameter space is smooth and continuous over space and time? But sometimes that is a merit. We just expect things to be very different even when they're next to each other in space. Or sometimes with new data, we can realize we were awfully wrong in the previous parameter space. So how do you comment on how much of that continuity that we want in the parameter space and hyperparameter space? Thank you.
So continuity in space and time, I think my basic take there always is if your gravitational constant depends on which planet you're on or depends on time, then you haven't gotten your theory right. So the first approach to me would be we should strive to get parameters that are invariant in space and time, or rather if you find variations in space and time, it's an indication that the model in which they're embedded is not universally valid. That's the first answer. I think but I think your question is going a bit further, right? It's maybe asking, I don't know if I'm putting words in your mouth. Was it?
Like sometimes mechanisms are just different, even with places are next to each other.
Yeah. I mean, again, in what we do, I would say if that's what it looks like, go back and try to understand what's wrong with the embedding physical biological model. I mean, in a climate system, if you end up with parameters that depend on space and time. And it's not uncommon, say, for a carbon cycle model. You have a lot of them that have parameters that vary with season, with year. And I mean, at some point, you can fit anything, right? We have a lot of data for a climate system, but in the end, we are actually in a data sparse regime. We have very few data relative to the number of degrees of freedom you can constrain. And if you end up with parameters that vary in space and time, then what do you do going forward in the future? How do you, what would you assume how they vary there? That seems to get complicated, and I'd rather not have that situation.
Okay, let's thank our last speaker. And